Hello students, now today we will discuss a very conceptual and important profile, that is as I have written, that is pivoted rod falling under gravity. Now let us see what is the situation. Now let me take a hinged or pivoted rod, this be the pivot, and let me consider a uniform rod. This rod is having mass m and length L. All right. Now see, from the horizontal position, this is the situation. Here I am releasing the rod. So what is supposed to happen? So it will come down. Why it is coming down? By virtue of gravity. Now let us discuss some conceptual feature or concepts regarding this. First of all, what are the concerned forces? As I have released, we can see from the center of mass or from the center of the rod being uniform, there must be force of gravity which is equals to, all of us know, that is mg. All right. Now don't forget that line of action of the force is this. And it's obvious to say that the rod is supposed to rotate about one end. So this is the axis of rotation, you can see. Now about this pivot, we know that there can be a force that appear at the pivot, at the support, we can say there can be force. But about this pivot, if we consider torque, so torque is having sense, torque produced by the force of gravity will be in clockwise sense. So therefore the rod will supposed to accelerate in clockwise sense. So what is the torque? You can see this is the line of action of the force and this is the perpendicular distance which is equals to L by 2. So what is torque? One can write torque clockwise, that is equals to force of gravity into lever arm or perpendicular distance, that is L by 2. Now students, about this axis, if the rod is rotating, we can say the moment of inertia of the rod about one end or axis passing through one of its end, we can say moment of inertia I is equals to, we know the formula, that is 1 by 3 m L square. So just after release, what is the expected angular acceleration of the rod? See, we can find alpha equals to torque upon moment of inertia, as we write acceleration equals to force upon mass, similar to Newton's law. So this is Newton's law, force equals to mass into acceleration or torque is equal to I into alpha, second law in rotation. All right. Now we can try this. What is torque? We have torque equals to mg into L divided by 2 upon moment of inertia, or you can multiply the reciprocal of moment of inertia, that is 3 upon ml square. So that will give us angular acceleration is equals to 3 times g upon 2 times L. So this is the angular acceleration just after the release. Now if someone asks what should be the acceleration of the center and acceleration of the end point, so one can see, students, if I draw the rod again, this is the rod and this is the pivot about which it is rotating. So we can see the center C and the end point E, they are going along circle of different radius. So what is this radius? It should be L by 2 being the center. What is the bigger radius of the end point circular path? It should be L. For a rotating object, we know the angular parameters are the same. For all the points, angular acceleration must be the same. But the linear parameter, that is linear acceleration, will differ due to different radius. So we can say that, what about the center? Center C. Now this be the center, the red dot I have shown, this is C, and the end point, say it is E. So don't forget that the C center is circulating in a circle of radius L by 2 and the end point with a radius of L. So, what is acceleration of the center? We can go for this. Acceleration of center equals to the corresponding radius, which is L by 2 times alpha, which is equals to L by 2 times alpha is, already we got the result, that is 3g upon twice L, that will give us the result 3g upon 4. Remember, this result is the acceleration is less than g. Now, what about the acceleration of the end point? Acceleration of the end point E. To get its acceleration, we can write r into alpha. So, we can go for acceleration of the end point is equals to corresponding r is L and alpha is 3g upon 2L. So, we are getting the end point is having acceleration 3 by 2 times g. Remember, this is greater than g. All right. Now, what are the forces on any part at any location? Basically, if you release an object, no other vertical force except gravity. So, gravity will put it downwards or accelerate downwards with g. Now, if you need acceleration greater than g, you need extra downward force. So, we can say the end point is under the influence of gravity as well as other parts of the rod must be exerting force extra downwards, therefore, the acceleration is greater than g. But what about the center? Center is accelerating downwards with less than g, that means there must be some opposition. So, students, if someone asks ki what is the force exerted by the other parts of the rod on a part very close to the center. Now, let us analyze. See, this is the rod. Now, let me consider a central part, say its mass is small m. It is accelerating downwards, it has linear acceleration of 3 by 4 into g, which is less than mg or accelerated to gravity. Now, forces are its own weight, that is mg, and there must be another force which is opposing its motion or it is against gravity. Let us take this force is F upwards. Now, Newton's law, we can write the driving force which is mg minus unknown opposing force Fu is equals to mass of this small part into corresponding acceleration is 3 out of 4 of g. From that we can estimate Fu. Fu is equals to, we can subtract to get the result mg upon 4. So, remember, the other parts of the rod must be exerting this upward force on the central part. In a similar way, if somebody asks you ki what will be the force exerted by the other parts on a very small portion near the end of the rod, let us consider the mass is small m. Do not forget its linear acceleration we already got, which is 3g upon 2, which is greater than g. So, therefore, students, we can say other than its own weight, that is mg, there must be some additional downward force, so that its acceleration must be more than g. So, we can expect other force, suppose F downwards. So, we can go for the force by writing the basic equation. The sum of the driving forces is mg plus another driving force is Fd, which is equals to mass into concerned acceleration, that is 3 by 2 into g. From that we can get what force the other parts of the rod is exerting on this small part. We can go for half times mass of the part into g by subtracting 3 by 2 mg minus mg. It is a very conceptual profile. You must remember this profile.